Hello, my name is Anna Fausta and I would like to present you in this short video what is the hidden terminal problem, a general solution to this problem called the RTS CTS Handshake, and another problem after that, the so-called exposed terminal problem, something to think about. So let's start. The hidden terminal problem is described by the following scenario. We have a node A which is trying to send something to node B. Not a problem at all, even in wireless communications. There will be some so-called transmission radius around that, where node A will be heard by anybody in this transmission radio. However, if node A and node B are alone in the room, then there should be absolutely no problem to communicate to each other. Then let's suppose that there is also another communication going on nearby. Let's say node C is trying to send a packet to node D. Also not a problem. There will be, however, again a communication radius here, a transmission radius around the sender. And let's say that node B is by chance in exactly that transmission radius. So in this case, C and D are not alone in the room, but B is overhearing the transmission of node C. And the problem arises if that happens at exactly the same time. So if node A is trying to send something to node B at exactly the same time as C is sending something to node D, B has a big problem. Because both transmissions will collide and he will actually not understand what's going on. He will not receive the packet from A, he will also not receive fully the packet from C, but some sort of chunks from both, and he will not be able to reconstruct that, and he will actually not be able to do anything else. So why is it called the hidden terminal problem? Because this one here, node A, is hidden from node C. So A and C, they cannot communicate to each other. They cannot arrange that I will talk first, you will talk next. And so that's why it's called the hidden terminal problem. And one possibility to solve this problem is to somehow let node B tell to everybody around around it that he will be or it will be receiving a packet soon, and that everybody else should be please silent in that time. That requires, of course, first A to send some sort of a preparation packet in order to say, hey, I have something for you, and then B sending out a packet or sending back a reply to node A saying that yes, okay, you're clear to send. And this is the so-called ready to send, clear to send handshake, or RTS, CTS for short. Let's look how that works. I have prepared here a small timeline, which is a very typical way of presenting several nodes in acting in the same environment at the same time to see who receives what at what time. So if you would like to implement this idea, in this case, node 3 would like to send something to node 2. So node 3 sends first an RTS packet to node 2 by saying in this way that I'm ready to send you a packet. Please shut down or make silent all of your neighbors so that they do not interfere with us. With that packet, not only that node 2 is now knowing that it will receive a packet, but node 3 actually shuts down all of the neighbors, all of its own neighbors. So node 4 will be now silent for some time in order to enable node 3 to be nicely sending its data. Node 2 now has, this will be this communication here, RTS. Node 2 has now to reply to node 3 with a clear to send packet, which means that I'm ready to receive your packet. This is this story here. And with that packet, not only that it says to node 2 that I'm ready to receive your packet, but it also shuts down node number 1. So these two will now, number 1 and 4, are silent, and they will not be interfering with the communication between nodes 2 and 3. Now, node 3 is ready to send the data itself. This is this thing here. So we send the data now over. And if everything goes smoothly, then node 2 will answer to node 3 with an ACK packet or acknowledgement in order to say, I have received the packet, I was under control, we are ready. This is the complete handshake, and of course we have to consider now what to do with nodes 1 and 4. At some point they have to become unsilent again, they should be allowed to talk again. This depends on the exact implementation of the network protocol. So what I have shown you here, the RTS CTS Handshake, is the basis for many MAC protocols and wireless communications. For example, Wi-Fi, for example, IEEE 802.15.4, and many others, just as examples. And the exact implementation of the network protocol will then consider also things like maximum data size. It will consider the exact frequency on which the network protocol is running, and many other details and parameters. And from all of these, you can actually calculate how much time at maximum two nodes need to communicate to each other. And after this time, the so-called backoff, you can restart your own communication. Of course, all of these things are a trade-off. You probably have noticed here already that now 1 and 4 have to wait for a pretty long time before they're allowed to send anything else again. And at the same time, that might not be necessary in all situations. One of these situations is the so-called exposed terminal problem, but before going into that, let us stick a little bit longer to this scenario here. You see here also that this maximum backoff, I have to consider that before allowing myself to send again something, but I will probably be wasting some time. So the trade-off here is always between trying to avoid collisions, one of the basic principles of MAC protocols, and at the same time using the resources as efficiently as possible. Why is it a trade-off? There is no perfect solution for that. There is no solution which will optimize the resources to the maximum and at the same time avoid any kind of collisions. So when you're maybe designing your own protocols, which happens, for example, in the area of sensor networks very often, or the Internet of Things, then you should always consider these two things. Like on one side, you would like to avoid collisions and problems, but you should also consider things like how often they could actually arise at all. And on the other side, you will always have the resource problem and whether you are efficiently using your own resources, not waiting too long for something which doesn't happen at all. But let us now go back to the exposed terminal problem. So, is there a possibility where we are overdoing it? And yes, it is. This is exactly the exposed terminal problem. Let's look what is happening here. Node B would like to send something to node A. This is okay. However, with the RTS CTS handshake, this communication will shut down node C. And what will happen is that it's not allowed now to talk, even if its own communication partner might be of course, node D, and in this case, they would actually have not interfered with each other. So these two communications are actually possible, but the RTS CTS handshake doesn't have a possibility to understand this, to predict this, and simply shuts down everything. This scenario is, however, extremely difficult to track and to understand in a real world problem, in a real world setting, because at the end you don't know where are your sensor nodes or nodes in general, and you also do not know where, even if you know actually where they are, the problem is that you don't know whether they will receive this packet or not, because the path loss is quite unpredictable and you might bump into some surprises. So in summary, I have shown you here the hidden terminal problem. I have shown you the RTS CTS handshake and how it solves the hidden terminal problem. We have discussed shortly the problems and the trade-offs between using resources efficiently and solving and avoiding collisions and problems in the network. And we have seen also what is the exposed terminal problem to always consider and have in mind whenever you're working with MAC protocols or you're designing even your own ones. Thank you very much.